have videos for 6.1, I have videos for 6.2, I have all of Calc 1 is on there from a previous semester. Last semester, actually. Not all of it, actually, from chapter like 3 something or 4 something on, because of the, because of us being shut down, right? So there is access to all that on my channel. But I'll post this up. Didn't I post up 6.1 for you guys?
I think so,
yeah. Yeah. All that stuff should be on Canvas for you guys. All right. All right, so let's do this. Let's do an example so you guys can see what I'm talking about, and then we'll go from there, okay? So looking at this, we're going to graph this problem. So the problem tells us that we have a function that is y equal to the square root of x, right? And we can do that. That's pretty dang easy to do. So let's say this is the x-axis. Let's say this is the y-axis. So if I go here like this, and this is what my root is going to look like, right? I'm going to find the area from 0 to 1, right? So the area from 0 to 1 is simply going to be this shaded, I don't want that, sorry. Is simply going to be this region right here, right? Now, what's happening in this problem, look at what it's saying. It's saying find the volume of the solid that's obtained by rotating about what?
The x-axis.
So we're going to take a rotation about the x-axis. So now we're taking this, this area, and we're going to rotate it about the x-axis. Now, something important to note here. As I rotate about the x-axis, right here, right? This is the x-axis here that I'm rotating on. Is there a gap in my shaded region? Anywhere along that red line? There's not, right? There's no gap. So that means that when I rotate this thing about the x-axis, it's going to be one solid piece, right? Since it's one solid piece, this is going to be called, and this is important, this will be the disk method that I'm going to use. Okay? That is the disk method. And there's a formula for the disk method, and it goes like this. It's pi times our function, and really it's the radius, squared times dx. Where dx is our gap in our x's, right? How thick our slices are going to be. And f of x is the radius. And I'm going to show you that real quick. I'm going to do this in a different color. So since I'm rotating about the x-axis, to get the area, I went this way, right? That was my slice to rotate through. Agreed? So I'm going to show you how this this formula becomes what it is. If I rotate about the x-axis, doesn't this thing form a circle? Do you agree? Right? So if I have this as my axis of rotation, and I have some curve, right? Isn't that curve going to go around the axis of rotation? So if it goes around the axis of rotation, what shape am I getting? We're getting a circle. So, look at what this is. Pi, what? Isn't this r? So it's pi r squared. Does that make sense?
Yes.
So here's the thing that's cool about this. So in this problem that we have, I'm going to go, oops, I want to be consistent, go back to black. I'm going to go from 0 to 1, right? Because that's what they're asking for. Of pi. Now, what's the height of my slice that I did? Not 0.5. I don't even know where you got 0.5. What's the height? What's the height of this right here? How far is it from the x-axis to this right here?
Oh, 3.
Well, no, don't be so specific, dude. And that's not 3. This is 1 right here. This slice... Okay, so hold on so you guys can all understand this. This slice right here is an arbitrary slice. It's just so you can see something. Basically, I have infinite many slices everywhere. Right? Those infinitely many slices are then rotated about the x-axis, forming an infinite many circles here. Right? Now, that being stated... How high is it from here to here? From here to here? From here to here? From here to here? From here to here?
The root of x.
It's exactly the root of x. So the radius is going to be the root of x. I'll bracket it to be consistent. Right? And then I'm going to have to square it and then dx for the slices that I'm doing. Now from here, we can clean this up. Pi can come out. I'm going to go from 0 to 1. Root of x squared is x dx. Then when I take the integral, I'm going to get x squared over 2 times pi evaluated from 0 to 1. And so I'm going to get 1 half pi. And I should go units squared because... Oh, units not squared. Units what? Cubed. We're talking about volume. But it's it's imperative that we understand that our cross-sectional slice is designed so we know what the height is going to be. This height ends up being the radius of the circle that's produced. Does that make sense?
Yes.
Are there any questions on this?
So you just, like, because I know you went from the root of x to x, so you'll always evaluate, like, inside those brackets before you take the integral?
Evaluate before the brackets? What do you mean?
Well, from the second line, pi, root of x, and then square, or is that just because those two canceled out?
Correct.
Okay.
There's no integration there yet. I've got a square before I can do the integration. Right? Right?
Yeah.
So that's why that's happening. But the whole crux to this is to understand that... Oh, sure. Do you want me to put those up right now? Did I not give you guys the blank notes for 6-2?
No, they're not up there, but it's okay. You can do it after.
Okay, I'll put them up after I'm done.
Yeah.
Okay, no
Yeah.
worries. Sorry about that.
Professor,
Yeah.
can you explain the setup again, like pi, f of x, and square?
Okay.
I'm kind of confused on that part.
So this is the disk method form. Okay? The first thing with the disk method that you have to understand is that there cannot be a gap at all in the interval of integration to the axis of rotation. So that's why I started off with, is there a gap to the axis of rotation? So was the blue shaded region gapped from the red line for the axis of rotation? The answer is clearly no, right?
Yeah.
So because of that, then that tells me it's a disk method. And so when I do a cross-sectional slice, this cross-sectional slice is going to be perpendicular to the axis of rotation. Because the circle that's being made is perpendicular to the axis of rotation. Does that make sense?
Yes.
So then this here, from the function to the axis of rotation, ends up being the height of the function. It ends up being the function because that's the height, that's the distance between the axis of rotation and the function. Does that make sense?
Yes.
Now, that piece ends up being the radius of the circle created. So then the area, the formula of the area for this, because we're forming a circle, is pi r squared. I could have made the area being made a square. But and there's problems that are like that, but I'm not doing that to you guys in this case. I'm just doing circles. Since I'm rotating around an axis, it's going to be a square. If I had said to you that I find the volume of a function, this curve to the x-axis in a square, then you would have to attack this a very different way. But I'm not doing that to you. All we're doing is rotations around axes. Okay?
Okay, thank you.
Now, does that make sense, the setup?
Yes, it does.
Okay. So this ends up being our solution. Okay, let me do another one. So now in this problem here, I'm saying find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0. Okay? So what that's telling me is this thing's going to go, it's a cube, so I'm going to go, I'll try to make my life as easy as possible. 1, 1, 2, 2, 8. And I'll only graph the top piece. The bottom piece is irrelevant in this case. Okay? That is y equals x cubed. Agreed? Here's the x-axis. Here's the y-axis. Then I'll do different colors for these others. Y equals 8 is this guy. Agreed? And really I should draw it in such a way that you guys completely see it. That's y equals 8. That's that line, y equals 8. And then we have x equals 0, which I'll do purple, which is this guy, right? Where do they enclose? Where do all three close up a region?
At the top right.
Okay, so just to make sure everyone's on the same page, it's this region right here, right? This is blocked up where, if you think of it, if fences dropped, that would be the only area where you couldn't get away. Does that make sense? It's enclosed.
Yeah.
Okay, which way am I rotating?
About the y.
About the y. So then if I'm going about the y-axis, I'm rotating this way, right?
Mm-hmm.
And for fun, I'm going to do this one so that it is a disk method again. So I want to show you something. I'm going to rotate, since I'm rotating about y, is there a gap to that purple line?
No.
There's no gap to the purple line. Since there's not a gap to the purple line, this is again a disk method. Does that make sense to everyone?
What would be the example of something that like does have a gap?
Oh, wonderful. I'm going to get to that. Patience, my friend. But I'll show you right now just for fun.
Okay.
If I had done it this way and rotated this way about the x-axis, would I have a gap to the axis of rotation from 0 to 2?
Yes.
Yeah.
Clearly. that is no longer the disk method.
Okay.
Now, because my rotation is about the y-axis, and I'm doing cross-sectional slices that are perpendicular to the axis of rotation, my slice must be perpendicular to the axis of rotation, so my slice has to be this way. Okay? Something important about this. What axis does that cross-sectional slice cross? I heard Jorge quietly, or Gerardo quietly. It's it's the y-axis, and since it's the y-axis, we know that this is going to be a dy integration. This one up here, when we crossed, my cross-sectional slice crossed the x-axis. This made it a dx. Okay? Now, since it's a dy, my integral is going to have to go from where to where?
From 0 to 2?
That's x's. Those are x's. It has to go from 0 to 8. And it has to go from 0 to 8 because we are talking about dy. And so the variables that we're going from are the y's. Does that make sense, Daniel? Okay. Now, since we're talking about dy, everything that we have as a function must be in terms of y's. So, I'm going to go pi. What is the height of that red line in terms of y? What's this black curve a representation of? X cubed. But I don't want x cubed. I want it in terms of y. So if I want it in terms of y, what would that be?
5. The third root of y?
The cube root of y, yes.
Yeah.
Does that make sense to everyone? Because y equals x cubed, to get rid of the cube, I have to go the cube root of y is equal to x. Right? Those two have the same graph. They are the same equation. Does that make sense to everyone? Okay. Now from here, I'm going to go from 0 to 8. I'm going to put pi out front because it's a constant. And I'm going to rewrite this as a power. So isn't the power going to be 2/3? Right? Y to the 2/3 dy? Okay. Now we need to do the power rule. And so the power rule is going to tell me, all right, I should have 5/3. This will be 2, oops. This should be 3/5, right? Times pi, evaluated from 0 to 8. Do we all agree?
Yes.
Okay. This will be 3 pi over 5 times 2 to the 3rd. That'll take care of it. So I'm going to get 2 to the 5th. 2 to the 5th is 32. And so I should get 96 pi over 5 units cubed. Do you agree with that? Make sense?
Yeah.
So if you have a cross-sectional slice that's going to cross the x-axis, you must have everything in terms of y. If it crosses the x-axis, the cross-sectional slice, you must be in terms of x. Got it? Yes, I am recording. you can tell this is a lift, right? This isn't something that's just straightforward today.
Oh, yeah. So I know that when 6.1, there were some of them where we set them equal to each other to find the bounds. Like if it's like the two y's. So we don't need to do that this time because we can just tell that it's like a y problem. Like how do we like?
We haven't gotten there yet, my friend. You're jumping the gun.
Okay.
In this problem, it's the bounded region, right? And we did do it in this one. Because if you look at it, y equals 8 was the upper bound on the y's. On the lower bound, it was bounded by x cubed and y and x equals 0, right? So x equals 0 and y equals x cubed are equal when? It's right there, dude. Where are they equal?
Oh, 0.
0 for y. And then when are these two equal? Y equals 8 and x equals 0. When are they equal? In terms of y, it's at 8. Right? Now, if I had done the slice this way, right? Like we had talked about, wouldn't we need to know what this x value is in order to know the bounds for this section? So we would have to set them equal to each other. We're just not there yet. I'm trying to make it stuff that's bearable before I just basically slap you guys across the face with some calculus. You know what I mean? It's like, okay, it's called scaffolding, right? Something that's a little bit comfortable where you're like, oh, he's pushing me a little bit. I mean, if you want, I could give you the hardest problem in this section to start, and you'd all be like, oh, I'm leaving. I'm done. So what I'm trying to do is slowly build you to it, okay? Why don't we do that right now? Why don't I cause you some stress? Not that you're not already feeling it, but hey. It's 2020, guys. Let's feel it. All right, so check this one out. So I'm saying the region R is enclosed by y equals x and y equals x squared, rotated about the x-axis, and then find the volume of the resulting solid. So, okay, cool. So I'm going to have one that's going to look like,
Cube root of 32 instead of multiplying it through.
I'm sorry, what did you say?
End of the last equation, I to the 5 over 3. So now you got this, but when I put to the cube root.
Oh, I did some just simple arithmetic. Here, watch this. Here's the way I look at this, right? So I would have gone 8 to the 5/3, correct? Okay. And most people would tell you, hey, you should go 8 to the 5th and then cube root that, right? I would never do it that way. I would do this. 2 to the 3rd to the 5/3 is going to be 2 to the 3rd times 5/3, which is going to be 2 to the 5th, which is 32.
Okay.
I just did it in my head. Sorry. But does that make sense, Jose? Make sense? All right. I appreciate you asking. It's worth going over. Okay. So y equals x is that line. Y equals x squared, and I want to make this a little bit more precise. And y equals x squared is going to look like this, right? Where this is 1, this is 1. What is the region that is enclosed, that is closed up? That if the walls fell like that and you were there, you couldn't run away.
from 0 to like it's like a good, that part right there, it's like going like up.
All right, so here, is it this section?
Oh, no.
Is it this one?
No.
This one?
No.
This one?
No.
That's it, right? That's the enclosed region. So this is what I'm looking to find. And what am I doing with it? Which way am I rotating it?
About the X.
So I'm going about the x-axis. So this x-axis is the y-axis, right? Is there a gap?
Mm-hmm.
Does everyone understand what I mean by there's a gap?
In this instance, I don't.
Okay, so check this out. So I'm going to go back to my red line. So this is the axis of rotation, right? Right? Okay. Is the blue, the thing that I shaded in, solid to the red line from the area that's shaded?
Mm-hmm.
Is that solid all the way down to the red line?
No.
No.
It is not, right? There is this gap here that causes me a problem, right? Because here, notice, here's the purple line for the axis of rotation. There, it's solid blue all the way along the purple line during the axis of rotation, right? In this one up here, same thing. It's solid to the red line from 0 to 1 for the rotation, right? This one from 0 to 8. But here, I'm obviously the enclosure is from 0 to 1. Is it solid with the red line from 0 to 1?
Oh, no.
The answer is no. So we have a gap. Okay? As soon as we have that gap, this is going to be called the washer method. Okay?
Do you have a favorite method?
Me?
Yeah.
No, I just look at the problem and see which one's the easiest one to do.
Same.
But that takes time and experience. You guys are going to be doing some stuff where you're going to be like, oh Lord, help me. But you'll be all right. We'll get there. It's just going to take some practice. Now, my slice now is going to have to go this way because remember, with both the washer and the disc method, we're going to want to be perpendicular to the axis of rotation. So what is this telling me? If I were to extend that slice, which axis would it cross?
X-axis.
Perfect. So that tells me that this one's going to be a dx. Does everyone understand what I mean by extending that axis, the cross-sectional slice to see which axis it's crossing? Is anyone unsure on what I mean by that?
I have a question. So when you're slicing it, it's always horizontal, right? Doesn't matter if the graph, it might be like...
In this case, this one's a vertical cross-sectional slice.
yeah, I'm sorry.
This
That's
one's
what I meant.
this one's horizontal. So it depends on what they're talking about in terms of axis of rotation. So
Okay, now it makes sense.
see how this one was y-axis, about the y-axis? So I had to have a cross-sectional slice that's this way because the rotation is that way. Always, 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 that line should form a 90 degree with the axis of rotation. Here, this one is 90 degrees to the axis of rotation.
Thank you, it's totally clear now.
Okay, cool, good. Now, in this case, it's very easy to see that the values are from 0 to 1, but I don't trust you guys. So what I'm going to do is I'm going to show the regions it's bounded. So x is equal to x squared, right? y equals x is equal to x squared, right? So what I'm going to do is I'm going to move that thing over. So I'm going to get 0 is equal to x squared minus x. Then I'm going to factor out an x. And so I see x is equal to 1 or x is equal to 0 or x is equal to 1. Those are the bounds of this thing. So I'm still going back to the stuff that we did in 6.1. Now, with the washer method, here's the important piece. What's going to end up happening is this, and I'll draw it so you guys can see. There's going to be two circles created. Okay? An inner circle and an outer circle. So, and I'll do it for you guys so you guys can see. We'll go Christmas colors, okay? The outer circle is going to be from the furthest point, right? The further function from the circle. And the inner circle is going to be from the closer point. So I want to show you why it's called the washer method. Ready? So what it's going to look like, so we can kind of picture it. And the shaded region gives us this. Well, what does that look like? Oh, well, if you've ever worked with like cars or built anything, that's called a washer.
Oh, damn.
Right? Right? You guys have seen a washer before?
Yes.
Donuts are cool too. I like them. I like donuts. But it's called the washer method because it looks like a washer. Okay? So here's the interesting thing about this. If I wanted to find the area of that washer, wouldn't I need the outer radius minus the inner radius? Right? So what ends up happening is this. The formula ends up being this. It is the integral of pi times the outer radius squared minus the inner radius squared dx. Or actually, it should be d whatever that thing is. D whatever. Okay? And you can see, it's basically, what that's telling me is, it's the outer circle minus the inner circle. Right? That's what the formula is telling us. Outer circle minus inner circle. So, in the problem that we have here, what is our outer circle? From the axis of rotation. So we know that the integral is going to go from 0 to 1. We know it's going to be pi. Now, the outer circle, notice that the outer circle, its radius is from the axis of rotation to the outer function, right? So what is the outer function in this region? Correct. I barely heard you, Gerardo, but I heard you. So it's y equals x, right? So the outer radius is going to be x and then squared minus what is the inner radius? Or what is the inner function?
Oh, x squared.
It's x squared, but then that has to be squared. And because we are vertical slicing, it's dx. We good? So much fun. All right, so now we can do this, right? 0 to 1. I'll move pi out front. And I'm going to get x squared minus x to the 4th dx. So that's going to give me pi times x to the third over 3 minus x to the fifth over 5, evaluated from 0 to 1. Agreed? Well, we don't need to plug in 0. That's nonsense. So we'll get pi is equal to 1/3 minus 1/5. And that's equal to 2 pi over 15 units cubed. See, these problems here that we're at now, you have to be engaged. A lot of my students would play music and be texting and doing stuff while they're doing their homework. And I'd always laugh. I'm like, what's funny about you guys doing your homework that way? You're going to make a lot of mistakes. And they're like, nah, we're used to it. We multitask. It's a new generation, Montiel. And I'd laugh. I'd be like, yeah, okay. It's cool. I have a master's degree in mathematics. And when I'm doing music and texting and doing things like that, I make mistakes with, almost 30 years of high level of math experience. But yeah, do you? Okay.
Professor Mateo?
Yes.
So if we were to turn this picture around so that the x is like on the y-axis, does that, when you throw the penny and it goes in a circle and it goes all the way down the middle, is that the type of shape it forms?
This one?
Yeah, if we flip the x with the y.
Okay, so I'll draw it for you. So it's like, you want me to draw it in a way that it looks vertical, up and down,
Yeah.
right?
Is that like when you throw the penny and the penny goes all the way around until it
Almost. So this one, the way it's going to look like is really what they do to you in bars. You guys don't know this. So if you go to a bar, so if I were to turn this thing sideways, instead of going left and right, I went up and down, it would look like this. Rotated. That's what it would look like. So what I'm saying about what they do in bars is they do this to you. Now it's a glass. But do you see what they've done to you? When you fill it up with your fluid, whatever your fluid of choice is, your glass deceptive?
Sure is.
It is.
You're not getting as much juice.
That's right. 50% ice too. That's true, man. But that's what it would look like. Does that make sense? So when you look at this thing, it would look something like this. Make sense? Silly drawing. But that's what it would look like if I turned that rotation, rotated 90 degrees. They do that with cereal or with like peanut butter and things like that too, right? So peanut butter used to be like this, the jars. And now if you look at them, it looks like that, but the bottom is rounded.
Oh yeah, wine bottles have it too.
They do that to wine too. So your eyes look different. When I was a kid, I'm no joke. This is just funny stuff. Cereal boxes were big and thick. So every box of cereal had 16 ounces in it. Now what they've done is they still have them the same height, but the depth is different. But you don't see that when you buy the cereal. So you end up with less cereal, but they still charge you the same amount. That's fine with me. That's funny. Okay, let's go on to the next problem. Enough of this conspiracy stuff. Yeah, it's to pour it, right? Ray, isn't that right?
Yes.
Yeah.
And the way it's stored.
Yeah.
Supposedly, quote unquote.
And you're always supposed to do it bottled down so the cork doesn't dry.
Yes.
All right, let's do another problem. Now I'm going to throw another spin into it for you guys, okay? So this problem, for this problem, it's going to look like the same picture, right? So I'm going to go, all right, here is y equals x. Here is my y equals x squared piece, right? So we know the enclosed region, right? So our enclosure is still that same piece. But now look what they're saying. What are we rotating by?
About the line y2.
Y equals 2 is now my line. Right? So if that's the line I'm rotating by, which way's my slice? Which way is my slice? Is it vertical or horizontal?
Vertical.
It's vertical. Good. It's this way. So which axis is it going to cross?
Oh.
So this has to be a dx. Is there a gap to the axis of rotation, the y equals 2 line?
Yes.
Yes.
Clearly. Good. Now for the hard part. Ready? There's an outer circle and an inner circle, right? Which would be the outer circle? So since it's dx, I'll save you. It's from 0 to 1. Right? We have our pi. What is the outer circle? Which function is further away from y equals 2?
X squared. Y equals x squared.
X squared, right? Cool. But here's the weird piece. Y equals 2 goes to where? The fact that y equals 2, doesn't that go all the way to the x-axis? Isn't that the distance? So this is 2 to the x-axis, but then I have to subtract x squared. Right? Because here the radius of 2 goes all the way to the x-axis. Do you guys agree with that? And then minus the x squared, so the outer radius is going to be 2 minus x squared, and then that has to be squared. Minus, what's the inner radius?
2 minus x.
Perfect. 2 minus x squared, and then this whole thing, dx. Are we okay with that? Is anyone not okay with that? Crickets? Okay. So then we can do this integral. It's pi 0 to 1. This is going to be 4 minus 4x squared plus x to the 4th minus 4 minus 4x plus x squared dx, which will be x to the 4th minus 5x squared plus 4x dx. Agreed? It's good?
Good.
Okay. So then that should be pi x to the 5th over 5 minus 5x cubed over 3 plus 4x squared over 2 evaluated from 0 to 1. And that's going to be pi 1/5 minus 5/3 plus 2. And that should be 8 pi over 15. And again, units cubed. Now, question for you, because we should play this game. If I had done the rotation over here and said it was y was equal to -2, what would the outer radius be? Because it totally changes the problem.
Y equals X.
So the x would be the outer, so that would be further away. So the integral would still go from 0 to 1. There'd still be pi, but now it would have gone x minus a -2 squared would be the outer radius, minus the inner radius, which would have been x squared minus 2 squared dx. Oops, minus a -2. Make sure I do that right for you. So what ends up happening is really I'm adding 2, right? So I just wanted to show you the difference. Above you subtract, below you end up adding. Can you guys see that? Just so you guys can, just in case you don't, from here to here, how far is that? Isn't that a distance of 2?
Yeah.
But then I'm adding that x height. So it's the 2 plus x to get all the way to here. Does that make sense? If I go from here, the problem is I go past it, and then I have to go back. So it's like you're traveling, right? So if you look at it this way, on the top one, it's like I traveled to the x-axis, but then I had to travel back to where y equals x. Do you see that? So it would be the 2 minus whatever the x traveled was. That's the top line, right? And then the other one would have been the 2 to the x squared, so it would be 2 minus x squared for the inner. Does that make sense? See how I'm going this way and then back? Right? In this case, the bottom one, I'd be going this, and then I got to go further. So this would be 2, this would be x, it's got to be x plus 2. Do you see what I'm saying?
Yeah.
The other one would be this, and then this little distance, this would be x, I'm sorry, this would be 2, and this would be x squared. So that would have to be x squared plus 2. Does that help you to see the radii?
Yes.
You sure? All right, I'm going to erase all this because I don't, too much work will make you all start tripping. So let's just focus on what we have. But if you want, you can rewatch the video and see that piece. But that's how I look at the radii. All right. Let's do another problem. So same picture. Same enclosure. But now where are we rotating by? aren't we rotating about x equals -1?
Yeah.
So now we're rotating here. This is the axis of rotation. So what should my cross-sectional slice be? Vertical or perpendicular? I'm sorry, vertical or horizontal? Which way?
Vertical?
Is vertical going to get me perpendicular to the axis of rotation?
No, horizontal.
It has to be horizontal. It's got to go perpendicular, right? If I was to extend it, it should go perpendicular to the axis of rotation. Does that make sense, Daniel? Okay, remember that. With disc and washer method, it's always going to be perpendicular to the axis of rotation. Okay? Okay. My region is this one. Right? Now let's see if we can do this together. Which one is further away from the axis of rotation? Y equals x or y equals x squared?
Squared?
The x squared. So that's going to tell me I have to go to here, right? And then I have to add to the x squared piece, correct?
Correct.
So this is 1 plus, because it's going in that direction. But I want it in terms of y, right? Because it has to be a dy now. Right?
Right, yeah.
Okay.
It's crossing one.
So what would the x squared, y equals x squared, be in terms of y?
Y squared?
Not y squared. Y equals x squared would be what? X equals what?
Square root of y.
Square root of y. So this would be square root of y. So we see that the outer radius is going to be 1 plus square root of y. The inner radius, it's going to be 1, right? We can see we haven't gotten there yet. To the inner piece, what's the inner piece going to be?
Just y.
Just y. So it ends up being 1 plus y. Okay? So my integral, I'm going to have pi outside, 1 plus root of y squared minus 1 plus y squared dy. What are the bounds?
-1 to 1.
How did you get that?
You have like the -1.
So you're saying you're going from here to, I'm sorry, are you saying here to here? Or are you saying from here to here?
That's the one I'm thinking. But probably the 0 to 1, right? Just because that's like how it's drawn.
So it's 0 to 1. Where is it bounded? It's bounded at 0 for y, and it's bounded at 1 for y. So this ends up being from 0 to 1. Okay. So now I got to expand this. So I'm going to get pi 0 to 1 of 1 plus 2 root y plus y minus 1 minus 2y minus y squared dy. So we can see this ends up being 2y to the 1/2 minus y squared dy evaluated from 0 to 1. So now when we integrate y to the 3/2, we should get 4 thirds, don't forget pi's out front, minus y squared over 2 minus y cubed over 3, evaluated from 0 to 1. Are we in agreement?
Yes.
So I should get pi times 4 thirds minus 1/2 minus 1/3, and that is 1 minus 1/2 is pi over 2 units cubed. How are you guys feeling?
Okay.
Not too bad.
Okay, good.
I think it's just understanding like the setup and then taking it from there.
Got it. All right. Do you want me to do another example?
Yes.
Yes.
All right. How about I let you guys try? I'll let you suffer. Okay, try this. Y is equal to 1 over x. Y is equal to 0. X is equal to 1. X is equal to 3. And then I want you to rotate it about y equals a negative 1. Let's see what you guys can do with this, okay?
All right.
I'll give you a couple minutes. How are you guys feeling?
Alright.
Isn't that a picture? So tell me about the shaded region. Yeah.
Well, I did the washer, I think. Don't know if that was right. But it was the -1 plus the 1 over x and then minus -1, I thought, because like the outer and the inner, and I thought the bounds were from 1 to 3, so maybe, and then I just kind of went from there.
Okay, so my shaded region is this one, right?
Mm-hmm.
Right?
Okay.
So, is there a gap?
No. Oof.
Where's the axis of rotation? I have the red line with the circle around it.
Y equals -1.
Yeah.
Yes, there's a gap.
This is y equals 1. This is called a gap. Right? Because the blue isn't shaded all the way to the red line, is it?
Oh.
So that means there's a gap. So because of that, doesn't that tell me that we have a washer? Oh, and this should be -1, right? I didn't put the negative there. Okay, so what is the outer radius? Oh, by the way, cross-sectional slice. I want to be consistent. What should I put? I'll use this line. That's the slice, right? So what kind of what is it? A dx or dy?
Dx.
Perfect. So my bounds then have to go from where to where?
1 to 3.
From 1 to 3. Okay, what's my outer?
-1 plus 1 over x.
-1 plus what?
1 over x.
Almost.
Minus 1 over x.
From here to the x-axis is 1, right?
Mm-hmm.
Plus
Oh, the gap.
1 over x.
Oh, so 2.
2.
Like it's like a distance of like from -1.
No. So cool. I see your mistake. Isn't the 1 over x? Isn't this distance from the x-axis to here?
Yeah.
Right? So this distance is 1 over x plus the 1. So really what it should be is 1 over 1, 1 plus 1 over x, that quantity squared, right? Minus, you ready for this? It's the gap distance, 1, and then the inner distance, which is what? Where does the bound start? Isn't this x equals 1? I'm sorry. Isn't that
Y equals 0.
oh, I drew it wrong. Dang it. It's y equals 0. This is supposed to I drew it wrong. Bummer. This is supposed to be y equals 0. So that is the x-axis. So I don't need this line. Stupid line. That is the x-axis. Right?
Yeah.
Okay, so what is the isn't it going to be 1 minus 0? Or I'm sorry, 1 plus 0 squared? Right? Is everyone okay with that?
So the distance, it's just 1, like it's the 1 plus 1 over x, just because you go up 1, just from negative 1.
Yeah, because I went 1. If I had that other line,
Absolute value.
so check this out. If I had that other line here, and let's say that this would have been negative 2, or let's just say that's negative 1 and this would have been a 1, okay? Just to change it a little bit more. I would have gone 1 plus 1, which would have made it 2.
Okay.
Does that make sense? But since it's at the 0, I thought this was 1 for some reason. I don't know. I was tripping. This gap is going to be this. So now when I go to do this, I'm going to write it down here so you guys can see. I'm going to get pi 1 to 3 of 1 plus 2 over x plus 1 over x squared minus 1 dx. Is everyone okay with that?
Mm-hmm.
Okay. Then I'm going to have to integrate, but I don't want to deal with negatives, so I'm just going to clean it up, okay? So I'm going to get pi 1 to 3 of 2x to the negative 1 minus x to the negative 2 plus x to the negative 2 dx. Because that way I can do power rule stuff to it, right? So I'm going to get pi times ln 2ln of x minus x to the negative 1. Agreed? From 1 to 3. So I'm going to get pi 2 ln of 3 minus 1/3 minus 2 ln of 1 minus 1. Agreed? So I'm going to get pi 2 times ln of 3 minus 1/3 plus 1. Agreed?
Agreed.
Okay. Which will give me pi 2 ln of 3 plus 2/3. Right? And really, I could clean that up if I wanted to. I could go pi ln of 9 plus 2 pi over 3 units cubed. Can you guys tell this is going to take some practice?
So how did you get? I mean, because I know that like the 2 over x, like that's like it's like the natural log, like 2 natural log. But if you got it into like 2x, like in the second line right here, 2x, like, and then you bring it like the negative to negative 1, couldn't you just do 2x negative 1 plus 1, or does that like just like screw it up? Oh. Okay.
Does that make sense?
Yeah, because then it's indeterminate.
Yeah, that's a special case. So that's where you have to know the antiderivative to that one. Cool, huh?
Yep.
All right, that's what I got for you for today. I want to do one problem for you from the exam. So this is different. So I'll stop recording here so I don't make the video all crazy. And then I'll post it for you guys to be able to see. So let me stop.